Better? Yeah, okay. So this is sort of the canonical model of mass and radius, and in this paper, she drew this blue line and said that is sort of the Earth-like line. And a lot of these planets, including Earth and Venus, went through this line, and then they sort of came up with this tautological saying that says planets inferred to be Earth-like are indeed Earth-like, and that has a lot of implications. So the question then we ask is, well, what does it really mean to be Earth-like? And then you can ask this even more existential question of, is the Earth even special, if we can just fit all of these planets with this curve? So I want to take a step back and actually look at the data we take for exoplanets. So here is a different way to plot a mass-radius model. So this is data, not a model. So this is radius on the x-axis and density, and I've color-coded the mass, and you can see we've got some variation. We've got some low density, high radius, and high density, low radius, and that may tell us something about the fraction of rock to core, maybe something about gas envelopes. It's very coarse in this model. Terrestrial planets are right here: Earth, Venus, Mercury, and Mars. We also have another data set that is sometimes overlooked, which is the actual composition of the host stars. So here is about 1,000 stars from a sample of F, G, and K stars. I've plotted magnesium silicon versus iron silicon. These are sort of terrestrial planet ratios. The sun is in blue. Red have observed planets. We can see some spread in magnesium to silicon and some spread in iron to silicon, and maybe this tells us something about the core size. If you have a bigger core, you should have more iron relative to silicon. And magnesium silicon is really the measure of what a planetary mantle should be made of, particularly its mineralogy. So really the focus of my PhD, which I just wrapped up earlier this year, was trying to connect these two data sets. Can we talk about how connecting the stellar data with the planetary mass radius data? So to do that, I want to then think about Earth-like planets, and I want to say, okay, well, we have this Earth-like model. Can we even fit the Earth to an Earth-like model? So if we're going to be extrapolating up to 5 Earth masses, let's make sure we get the Earth right. So I'm going to put this in mass and composition space, because connecting stars and planets. And here's the Earth at about a silicon to iron ratio of 1 and 1 Earth mass. Ignore that blue line for now. But if we were to see the Earth, we would observe the Earth, we wouldn't be able to take its spectra. We would have to take the sun's. So the sun has a slightly higher silicon to iron ratio. So we're just going to look at the sun for now. And this is the planet we're going to model. We're going to model a 1 Earth radius planet. And so this is where you should pay attention to the blue line. If you actually modeled a 1 Earth radius planet using what we know about the Earth as Earth scientists, you overestimate the mass of the Earth by about 13%. So that Earth model, that canonical Earth model, is wrong. And I can tell you some reasons why. So one thing is they don't have an upper mantle in their model. That seems obvious. They just basically extrapolate Bridgmanite all the way up to the surface. And they use a solid iron core, whereas we know, for the most part, the core is liquid. And we should expect liquid iron cores on most terrestrial planets, just if you look at the phase diagram of iron. Terrestrial Earth-sized planets and up. And we'll keep the magnesium-silicon ratio of the mantle at 1. That just makes it easy. So if you run this model, my model, you actually still overestimate the mass of the Earth by about 5%. But that's good, because we also were adding details to this spherical cow model. I'll skip that. So one thing that makes a difference in the Earth's mass is that the core is not pure iron. It has some amount of light elements in it. And you can choose your favorite light element. So carbon and oxygen will definitely change the mass of the core, but it does not change the silicon to iron ratio that much. Sulfur has a bigger effect. Silicon has a very large effect because it's in the numerator and somewhat in the denominator. But you can see that we can change the mass of the planet as well as its silicon to iron, or our inferred silicon to iron ratio. And the other thing we can, so you can choose sort of an optimum from mineral physics of what we think the Earth's core is like. So let's benchmark to the Earth and sort of compare across. So this is some amount of silicon and oxygen. We can also change the magnesium to silicon ratio of the mantle and see how that changes our silicon to iron ratio in the mass. And really from this you can see core density changes has a large effect on silicon to iron and mass, whereas changing the magnesium-silicon ratio of the mantle has a small effect on mass, but a large effect, or a somewhat effect on silicon to iron. And there's the sun, which falls nicely in my model. And if you take an Earth model, which is sort of by this green box, some core density between about 5 and 10% less than iron, and a magnesium-silicon ratio of the mantle, which you can look at mantle xenoliths and maybe get an idea of the mantle's magnesium-silicon ratio, falls in that green box. So in this plot, I've reverse engineered the Earth using the sun. That's pretty cool. So in this sense, for my really coarse order of magnitude model, the sun is a good proxy for the Earth. So if you're going to tweet, that's what you should tweet. So if you can expand that, Earth is great, but let's talk about Earth-like planets across the mass radius spectrum. So here is radius versus silicon to iron in astronomer units, and I'll tell you why it's in astronomer units in just a second. And what this says is if you have planetary radius, which is what you would get from a transit method, you have to actually follow up to get a mass measurement. While you're there, you might as well measure the stellar composition and get a silicon to iron ratio. And from that, you can actually, these contours are contours of constant mass. So you can run across, say, oh, well, there's my planet. And then this Earth-like range is just the core size that is bound by the sun and the Earth's true silicon to iron ratio. So next up is, well, is that a true assumption? Is the sun's composition a good proxy for the Earth from a chemical perspective or from a cosmochemist's perspective? So this is how I defend that. So this is the photospheric abundance versus the C1 chondrite, which is one Earth model for what the Earth might be made of. So iron and silicon, magnesium are all elements that are refractory. And what that means is if you have a gas, these will condense first at very high temperatures. So in this one-to-one line, which is in green, you can see those three elements falling nicely on it. Oxygen is a little bit above, and I'll talk about that in a second. So you can then make the next step and look at the actual Earth abundance for some Earth compositional model versus photosphere. And again, those are pretty close to that one-to-one line, but oxygen is not. And that's important because the Earth is not made of just refractory metals. They are oxidized species. So if you were to use the sun's oxygen abundance, you would actually overpredict the total oxygen budget of the planet by a factor of 8 or so, which means you would oxidize everything, there would be no core, and that's not the planet we live on. And that kind of makes sense. Oxygen is a volatile element, you would think of. So we need to make some correction on the oxygen abundance to basically turn it into what I call refractory oxygen, to say this is the oxygen abundance that, or some approximation of the oxygen abundance of a planet. And I'm always sticking with the Earth because I want to benchmark to the Earth and then expand that model outwards to make actual comparisons across the exoplanet data set. So to do that, you need to create the phase diagram for a solar gas. And this is, you may have heard of it also called condensation sequences. So you would take a very hot gas and let it cool down and see which solids form first. So I show aluminum, even though aluminum is a dinky element with regards to planets, it's the coolest phase diagram because you can see everything that goes on. So you start up really high where you have monoatomic gases, then you start forming more complex things like aluminum gas and ALOH, and then the solids start forming. You get things like corundum, a really refractory mineral, but eventually it all settles down to things like anorthite. But this anorthite here says that for every aluminum atom I may form a planet with, I carry 8 moles of oxygen. So then you can start playing stoichiometry games. So here is probably which was surprising to me is not often thought of, the oxygen phase diagram. So here you start high and you get these CAIs, which are these dashed lines, but then really things we think about form terrestrial planets. Forsterite, enstatite are the main hosts of oxygen. In total, about 23% for this solar model fall into, of oxygen is refractory. So that would be your sort of an estimate of your oxygen budget with which to build planets, which is my very simple super duper planet. If you have those 4 elements and later 2 more, but for the most part, you can describe the Earth really well in its structure, in its mineralogy with those 4 elements for the bulk of the mantle and the upper mantle. So let's look at it in a different way. So this is the same 1,000 stars I showed earlier, just on a ternary. So here's iron, magnesium, and silicon. The red is the same data set I showed earlier. The black are the Kepler stars. And there's the sun sort of right smack in the middle. Now, so you can run, now you've got iron, magnesium, silicon, and oxygen. You can calculate the weight percent of the core, or the core mass percent, which are these contours here. So the sun, great, falls exactly kind of where we expected, between 30 and 35 mass percent of a core. The real answer is about 33, 32. So good, now shown, that their stellar diversity and planet diversity are linked. So I would predict that little black spot, if it had a planet, has a very high core fraction as well, mass fraction. And there may be populations. It's a little hard to see here, but there's a bit of a lobe, and then you've got sort of this spread. What do those planets look like? What's the true diversity? So this is something where I'm giving a talk at an astrobiology conference, but I think of things in planetary diversity, not planetary habitability. I want to understand how likely are Earths. So that's because, now I'm, of course, completely talked myself into a corner because I want to talk about habitability now. So this is a really crummy picture of tectonics. So if you shut off tectonics, of course, it does a great job of regulating the atmosphere, so you're pumping carbon in, and this has, of course, heat problems for how your core crystallizes. So one thing I'll talk about really quickly is one thing that controls tectonics, which may control habitability, is buoyancy of the plate. So as a plate goes down, it undergoes a phase transition, it becomes a really terrible term, negatively buoyant, and keeps sinking. And it's one of the things that helps power plate tectonics. It's also a purely chemical process. Well, chemical and mineral physical property. So I want to know, within this sample, which of these compositions are likely to produce planets that can undergo that phase transition and become successfully negatively buoyant and keep sinking. So this is sort of big data planetary science and just asking the question, how common are negatively buoyant plates? I'm not saying whether plate tectonics is occurring, I'm just saying if it did, what is the likelihood? So we need to melt everything and basically get an idea of what the basaltic crust is, and then make the phase diagrams. So here is your basalt phase diagram. This is for our Earth model. Again, benchmarking to the Earth. And here's your basalt. You integrate the differences in density down at whatever depth you want, and you can calculate a buoyancy force. So here is, and these are preliminary results. They're almost done. The paper's written. We just need to finagle. So this is magnesium silicon versus net buoyancy force running through a lot of chemistry that if you're interested, I can talk about. And I've made a line for the model Earth, and only about 5% of that total 1,000-star sample actually works to create negatively buoyant plates. So I'll leave it here. My real point, which I've underlined here, is that Earth-like does not mean compositionally similar. It may not even mean the atmosphere is the same. It behaves like the Earth, because tectonics, dynamics are really what's powering all of this. And we all need to work together to solve this problem. So thank you.
All right, question already.
Thank you. Regarding plate tectonics and also
Sure.
Buoyancy of mantle material, how do you rectify similar chemical composition between Earth and Venus and the current
Excellent
condition?
question.
Thank
So Venus is always going to dog this question. If the sun's composition is similar, then Venus and Earth should be exactly the same. So right now, we're working on getting mixing to understand maybe something Venus or Earth formed slightly differently, or we're not taking into account actual disk mixing, so something like that. And then if we see that that doesn't work, we'll add extra details of history, what happened to make, and sort of it's constraining Earth and Venus from the outside, like what doesn't work versus what did work, and we'll add details as we go. But I am really interested in Venus, and I think thinking of Earth and Venus as sort of the ideal and not ideal exoplanet and understanding the differences is a really profound way of understanding all of exoplanetary science. So.
All right, Brandon. Excuse me, sorry.
Yeah, so is there any worry that the dynamics, like how you form these planets, sort of obscures the link between stellar composition and planetary composition?
Yeah, so right now I'm working, I just started my postdoc working on integrating, so the condensation sequence code I've written with mixing models to sort of get an idea of feeding zones. So one of the things in this this plot here is I've bound by the Earth and the Sun, but Venus doesn't actually work unless you use a slightly higher magnesium to silicon number for the mantle. And that's interesting because in the oxygen phase diagram, you get something of Mg over Si of 2 condensing before Mg Si of 1. So if you preferentially mix from higher temperature closer to your star stuff, you might expect high MGSI. So that's where figuring out adding a dynamical component, saying this is where it fed from, here's what the chemistry of the stuff it formed from. Now run the stoichiometry and figure things out. So that's what we're doing right now.
All right, let's thank Cayman again.
Thanks.